Hello, everybody. Professor Barlow, Northampton Community College, Physics 215. We're going to be doing Chapter 18, which is the kinetic theory of gases. This chapter is fairly light on calculations. It does have quite a bit, well, it has more theory than it does calculation. Is probably a better way to say this. So we're going to go over the kinetic theory of gases. In this, sorry, let me get my screen sharing here worked out. There we go. Okay. So we are going to talk a little bit of how ideal gas law and the molecular interpretation of temperature. We're going to talk about distribution of molecular speeds. Now, people who have had a statistics class, some of this is going to tie back into that. If you haven't had a statistics class, no worries. We'll go over the things that you need to know from a physics perspective. Real gases and changes of phase. We're going to talk about vapor pressure and humidity. Now, the last three sections, van der Waals equations of state, mean free path, and diffusion, those are asterisk sections in the text, and we are going to be skipping those. Okay, so you're going to see me skipping some slides like I have in the past. Assumptions of kinetic energy. Okay, now not all of these assumptions are really accurate, but they help with an initial understanding of the subject. And as you move forward, if you start digging a little deeper, it's like anything that we've gone over, like projectile motion. We ignore drag in projectile motion. Well, drag is real, and in real life, it really can't be ignored. But for the first blush at looking at the subject, it doesn't have a tremendous effect, so we kind of ignore it. So in our initial blush at this for kinetic theory, there is a large number of molecules moving in a random direction at a variety of speeds. So that may or may not be true, but that's a fairly safe assumption. The molecules are relatively far apart. The molecules obey classical laws of mechanics and interact with each other only when colliding. Again, may or may not be true, but these are the assumptions that we're making, and that we're assuming that the collisions are perfectly elastic. Okay, so the force exerted on the wall by the collision of one molecule is given by the equation shown below. Then the force due to all of these collisions is you're taking the number of those molecules and multiplying it by what you did above. The average of the squares of all of the speeds in all three directions are going to be equal, so the pressure is given by this equation. Okay, if we rewrite it, we end up with an equation for translational kinetic energy for the molecules of an ideal gas. 1/2 average mv squared, or 3/2 kT. Okay. So molecular kinetic energy, they want us to determine average translational kinetic energy of a molecule of an ideal gas at 37 degrees. Okay. In this equation, K is that Boltzmann's constant from the previous chapter. Okay. So calculate molecular kinetic energy. Okay. So switch over to a whiteboard. Okay. So K is Boltzmann's constant. The T, right? So the uppercase K is kinetic energy. 3/2 lowercase k, which is the Boltzmann constant, and T. The T is going to be given in kelvins. Okay. So 37 degrees Celsius is 310 Kelvin, so 37 plus 273. So 3/2, the Boltzmann's constant is your 1.38 times 10 to the minus 23rd joules per Kelvin. So our kinetic energy is typically in units of joules. We have Kelvin in the denominator here, and we have 310 Kelvin, which is 37 degrees converted to Kelvin. So your Kelvins will cancel, and you'll end up with kinetic energy. So the kinetic energy is 6.42 times 10 to the minus 21 joules. Now that is for 1 mole. This is just for 1 mole. They're asking for average translational kinetic energy of molecules. Okay, so to go from joules per mole in 1 mole, we use Avogadro's number, 6.02 times 10 to the 23rd molecules per mole. So really, this should be joules per mole. And in the molecule, there's 3,860 joules of kinetic energy in an ideal gas. So now to calculate the average speeds in those previous equations on the previous slides, there's 2 main ways that we can calculate speed, okay? One is just an average, and we'll talk about that in a second. But one is root mean square, which is RMS, which is what this little RMS stands for, okay? RMS is the root mean square, all right? And RMS could also be 3 kT over m, over the mass, okay? So to get root mean square, right, you can get the square root of the averages, which is what root, you're taking the square root, mean, average of the squares. Or if you knew the temperature and the mass, all you'd need is Boltzmann's constant and be able to derive it that way. So there's more than one way to do this. So let's take a look at that, okay? Speeds of air molecules. So if you're given just the molecule and the temperature, and you weren't given a data set of speeds, you would have to use this equation right here. So we're going to calculate root mean square. What is the RMS speed of air molecules, O2 and N2, okay, at room temperature? So the first thing we need to do is we need to take a look at the masses of your oxygen and your nitrogen. We know that 1 U in mass from the previous chapter is 1.66 times 10 to the minus 27 kilograms. To determine the mass of the O2, we know that 1 is 32, or I'm sorry, 1 is 16. So 2 molecules it would be 2 times 16, which would be 32, times the 1.66 times 10 to the minus 27 kilograms. You end up with 5.1 3 times 10 to the minus 26 kilograms for your mass of your oxygen. The mass of your nitrogen is 2, 1. Nitrogen is 14. So 2 of them would be 28. 1.66 times 10 to the minus 27 kilograms. And hopefully some of this is a bit of a review from a chem class that you either took in high school or at the college level. Again, minus 26. So this is 26 kilograms. Okay. So for O2, the root mean square for O2 molecules. So the equation that we had is VRMS is equal to the square root of 3 KT, where K is your Boltzmann's constant and M is your mass. So this is the equation that I'm using. So 3, Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per Kelvin. The temperature that we were given was 20 degrees C, but we want it in Kelvin. Whoops, it's 273. 273 plus 20 is going to give me 293. And then for our oxygen, we had 5.3 times 10 to the minus 26 kilograms. So our VRMS for the O2, 480 meters per second. That's how fast the molecules are moving around inside pure oxygen. Let's take a look at the N2, nitrogen. 3 times 1.38 times 10 to the minus 23rd joules per Kelvin. And 273 plus 20 is 293 Kelvin. It's the same thing. Now I'm going to use the mass of my nitrogen, which is 4.6 times 10 to the minus 26 kilograms. So the root mean square velocity of the nitrogen is 510 meters per second. Now that's how fast the molecules are moving around in the gas. Another example. Less gas in the tank. A tank of helium is used to fill balloons. As each helium balloon is filled, the number of helium atoms remaining in the tank decreases. How will this affect the RMS speed of the molecules remaining in the tank? Well, what does RMS speed depend on if we're given the temperature and we're given the number of, or the mass, right? So the mass is not going to change. If the temperature remains the same, the Boltzmann's constant is just that. It's a constant. So if the temperature remains the same, the RMS speed is not going to change, okay? So the speeds inside the gas are not going to change. Well, let's take a look at an example where we're not given the gases, but we're given a data set of speeds. So they want us to determine average speed and RMS speed of 8 particles that have the following speeds: 1, 6, 4, 2, 6, 3, and 2, and 5 meters per second, okay? So average and RMS. Average is just what it sounds like. It's just a simple average. So we have 8 particles. So average. So you have 1 plus 6 plus 4 plus 2 plus 6 plus 3 plus 2, oh, plus 5. I missed one. Plus 5. And those are all in units of meters per second. And there's 8 of them. So simple average velocity is 3.6 meters per second. So if I'm given a whole bunch of data points, a lot of times in statistics or in academic work, you will look at the results of something and then you will look at the RMS, the root mean square, and you might be able to draw some determinations from it. So sometimes you'll see this in research. So you will take all of your data points, all of your velocities, and square them in the numerator. Okay. 6 squared plus 4 squared plus 2 squared plus 6 squared plus 3 squared plus 2 squared plus 5 squared. Did I get them all? 1, 2, 3, 4, 5, 6, 7, 8. Yes, I got them all. So those are all my velocities squared. I'm taking the average, so I square all my velocities in the numerator, divide it by the number of data points, then take the square root of it. So the velocity RMS, not using the previous equation, but using a bunch of data points, is 4.0 meters per second. So slightly different. So what does that mean? Well, in terms of molecular distribution of gases, let's take a look and see what that means. Might mean different things for different subjects, but molecules in a gas will have, they're not all going to have the same speeds, just like grades on a test, okay? If you were to plot a whole bunch of data points, okay, you could end up with a distribution. So the relative number of molecules and the speed. So if you plotted the speed on your x-axis and the relative number of molecules on your y-axis, okay, your average, right, would be on a Maxwell distribution, would be slightly to the right, whereas your most probable speed, right, is here, which is the peak of your distribution. So your average is here, and then your VRMS is here. V sub P is your most probable speed. So the distribution of molecules in an ideal gas is shown by this Maxwell distribution. Note that the average and RMS are not at the peak of the curve. That's because the curve is skewed to the right, so it's not symmetrical. The peak of the curve is the most probable speed. Now, in other types of analysis, there's other types of distributions, okay? So you've all heard of the bell curve. That's what most grade distributions look like, okay? A Maxwell distribution depends only on absolute temperature, okay? This figure, what it shows is the distributions for two different temperatures of the same gas, right? One is at 0 C and one is at 37 C, okay? So take a look at that and notice that for the two different temperatures, at the higher temperature, the whole curve just kind of shifts to the right. So it's the same distribution, but it just kind of shifts. So the molecules are going to chemically react only if the kinetic energy is great enough that when they collide inelastically, they squish together, right? Inelastic. The minimum energy for that to happen is called the activation energy. And the velocity at which this happens is this VEA. EA is the activation energy and the velocity is that velocity. So it's specific for different types of reactions. So the number of molecules with energy greater than EA is the area under this portion of the curve. So determining V and V sub P, so they want us to determine V and V sub P, the most probable ideal speeds in an ideal gas. I'm not going to ask you to do this type of proof on a test. I think it's more important that you know how to get VRMS based on the two methods that we showed. One, if you were given information about the gas and you could determine the masses, or if you were given a data set of different speeds. Okay, if you want to look at the proof for this, it's in the textbook on page 481. So you have these PV diagrams for different types of gases. So a PV diagram is pressure, volume pressure. Volume is on the x-axis, pressure is on the y-axis. The curves below represent the behavior of the same gas at different temperatures. The cooler it gets, the further it gets from being an ideal gas. So curve D, for example, right here, the very bottom one, it actually becomes a liquid, right? It has a liquid vapor region. So it goes back and forth between being a liquid and being a vapor. So the gas becomes a liquid, it begins condensing, it begins becoming a liquid at B, right? Anything to the right, it's a vapor. It starts becoming a liquid at B, and then it becomes a complete liquid at point A. Point C, right? Point C is it's called a critical point. Anything lower than that critical temperature, the gas starts becoming a liquid. So anything below that critical point, you have a gas that's starting to condense and become a liquid. So the critical temperatures, that gas can liquefy if the pressure is sufficient. Above it, no amount of pressure is going to suffice. So you need a certain amount of pressure, but the critical temperature for water in degrees Celsius 374, Kelvin 647, the critical pressure is 218 atmospheres, and then that information is given for a bunch of different gases. A pressure temperature diagram is also called a phase diagram, Okay, temperatures on the x-axis, pressure in atmospheres is on the y. Temperatures are given in degrees Celsius. So the phase diagram of water is what's shown in this figure. Okay, it shows all three phases of the matter. We're ignoring plasma, so we're just looking at solid, liquid, and gas. So solid liquid transition is the melting point. Or going the other direction, it's the freezing point. Liquid vapor is the boiling point, or going the other direction, it's condensing. And solid to vapor, jumping from one to the other, that's called sublimation. You can have sublimation for certain things. If you think of dry ice is a solid, and when it's out at room temperature, it immediately goes to vapor. That is sublimation. The opposite reaction for that, it's not in the text, it's called deposition, if it goes from a gas right to a solid. Okay. So you have a solid region, liquid region, and a vapor region. Depending upon where you plot your temperature and pressure will tell you whether or not you're a solid, liquid, or gas. There's one point at which the substance can be solid, liquid, or gas, right? And that's called the triple point. It's the only point where all three phases of matter can coexist in equilibrium, okay? So here's a phase diagram of carbon dioxide, solid, liquid, and vapors marked. You got your triple point. You have the critical point. Critical point for water is here. You can see 218, 374. Carbon dioxide. So, and again, triple point is where all three phases can coexist in equilibrium. If you have an open container of water, the water can evaporate. So rather than boil away, it's still there, but it's in vapor form. It's not being dispersed out into the atmosphere or into the room. The fastest molecules are escaping from the water surface, so evaporation is a cooling process as well. The inverse process is called condensation. When the evaporation and condensation processes are both in equilibrium, the vapor just above the liquid in here is said to be saturated, and its pressure is saturated vapor pressure. So saturated vapor pressure will increase with temperature. Okay. So as temperature goes up, your saturated vapor pressure also goes up. So here you got a picture of liquid boiling. A liquid boils when its saturated vapor pressure equals external pressure. So the boiling bubbles of water vapor float upward from the bottom where the temperature is the highest. Partial pressure. Partial pressure is the pressure each component of a mixture of gases would exert if it were only if it were the only gas present. Okay. The partial pressure of water in the air can be as low as 0 and as high as the saturated vapor pressure at that particular temperature. Relative humidity, okay, so meteorologists determine relative humidity by they take the partial pressure of water at a particular temperature and divide that by the saturated vapor pressure of water multiplied by 100%. So it's a ratio of partial pressure of water versus saturated vapor pressure of water. Relative humidity, it's a measure of how saturated the air is. So how much water is there in the air? So this example, relative humidity. On a hot day, the temperature 30 degrees C, and partial pressure of water vapor in the air is 21 torr. Okay, what is the relative humidity? Okay. So what you would need to do this problem is, in addition to knowing what they gave us, that at this 30-degree day, you're at 21 torr, right? You need to look up, or you'd need to be given, the vapor pressure at 30 degrees C is 31.8 torr. So if you have your two pressures, it's just the 21 that it is related to the 21 or the 31.8, which is the saturated vapor pressure. Sorry, saturated vapor pressure. So it's just a ratio. Times 100%. So this works out to be 66%. Okay. So when they say the relative humidity on the weather forecast, that's what they're referring to. So when the humidity is high, it feels muggy. It's hard for any more water to evaporate and get into the air. Dew point is the temperature where the air would be completely saturated with water. So dew point is the temperature at which the air would be completely saturated. If the temperature goes below dew point, then you'll either get dew, fog, or rain. Dryness in the winter. Why does the air inside heated buildings seem very dry on a cold winter day? Well, heating the air is going to decrease the relative humidity, and the partial pressure of the water is going to stay the same. So you're reducing that ratio. Okay. That takes us to section 18.4. 18.5 deals with the van der Waals equations of state. You are not responsible for this. If you want to look over it, you're welcome to. You are not responsible for that, free path, or diffusion. Diffusion is kind of an interesting subject because even without stirring, if you put a little bit of dye or something in water, it'll disperse and it'll make it turn pink. That process is called diffusion, and it also happens in gases as well. So you have areas of high concentration and low concentration of whatever it is, it will diffuse. Average kinetic energy of molecules in a gas is proportional to temperature. Anything below that critical temperature, a gas can liquefy or condense if the pressure is high enough. Triple point is where all three phases of matter can coexist in equilibrium. Evaporation occurs when the fastest moving molecules escape from the surface of a liquid. Saturated vapor pressure occurs when the two phases are in equilibrium, liquid and gas. Relative humidity is the ratio of actual vapor pressure to saturated vapor pressure at a particular temperature. Van der Waals we're ignoring, free path we're ignoring, and diffusion we're ignoring for an introductory class. And that is the end of chapter 18. So only two more chapters to go, chapters 19 and 20. As always, please come to class prepared with any sort of questions, comments, concerns, and look forward to wrapping up the semester. So have a great day / evening, and we'll see you for the next session.